Welcome to Master Apache MADlib, a series of short videos designed for data scientists new to MADlib and for aspiring data scientists. I'm Charles Killam, and I will be your guide for this video on support vector machines. If you're not already familiar with MADlib, MADlib is a library of machine learning algorithms that are open source, utilize massive parallel processing or MPP, runs functions where the data resides, so it's in database, and uses SQL to execute the MADlib functions. MADlib runs on open source Apache Hawk running on Hadoop, Greenplum database, and Postgres. As you can see from this slide, MADlib consists of a variety of popular machine learning algorithms and statistical functions such as principal component analysis, random forests, support vector machines, and a popular time series analysis function called ARIMA. So what are support vector machines? SVMs belong to the supervised learning category of machine learning. All this means is that there are two steps to making predictions. First, you must build your model by training it with known classification values. Second, you apply the model built in the first step on new data to test the effectiveness of that model. Typically, SVMs are used for binary classification. However, they can be used for multi-class classification and regression. SVMs are a great choice for handling noisy data and works well with very large data sets. This slide provides a visual representation of what an SVM looks like, along with some terminology. The primary thing to focus on is this dividing line, commonly referred to as the decision boundary or the maximum margin hyperplane. All the points lying on one side of the decision boundary receive one classification value, and all the points lying on the other side of the decision boundary receive another classification value. Data points closest to the decision boundary make up the support vectors. Sometimes, however, the decision boundary is not linear. MADlib's SVM algorithm supports nonlinear SVMs by either specifying a Gaussian or polynomial kernel trick. Towards the end of the video, I will show a simple change in syntax you make to get a nonlinear SVM. So for this example, I used FAA data, specifically from the on-time performance table, and you can get more information about this data by going to this link. In order to have data the SVM algorithm can process, various transformations were needed. Here I provided a couple of examples, such as performing updates and creating dummy variables. I also used logistic regression to get a sense of significant independent variables to pass to the SVM algorithm. Included in this MADlib series are other videos on creating dummy variables and logistic regression if you'd like to know more about how to execute these functions and what they do. Here we see the table and the data after various transformations. SVM expects numeric data and does not handle these categorical values very well. As such, I will pass to SVM the month and day of week dummy variables shown here at the bottom of the slide instead of these original categorical variables shown at the top. So with our data in the correct format, we're now ready to look at the syntax and output of the SVM training step. Near the top of the slide, we see the syntax for building an SVM model. There are 4 required arguments to the SVM_classification function. They are source table, model table, dependent variable name, and the independent variable list. There are also some optional parameters that will either be discussed towards the end of this video when I show example syntax for nonlinear SVM model building, or that can be researched by going to the MADlib documentation link provided at the end of the video. So the first argument passed to the SVM classification function is the source table. This is a table that contains training data. Then you specify the name of the model table. This is the name of the table to be created to hold the SVM model. We will take a look at the contents of the model table on the next slide. The next argument provided is the name of the column that holds the known labels for the dependent variables. And the last argument provided is the independent variable list. These are the variables that support predictions made. Note that the variable list, or the independent variable list, uses an array. This may differ slightly from how you specify variable list in other MADlib algorithms. Also note the dummy variables such as month_April. And note that these dummy variables have double quotes surrounding each column name. The original categorical values all began with an uppercase. Dummy variables are created with the following naming convention. The name of the original column name, underscore, followed by the categorical value. Hence why we see an uppercase in the name of the dummy variable. Depending on how your database is set up, you may need to use double quotes around the dummy variables. Otherwise, you may receive a column does not exist error message when running the SVM classification function. In this example, I used 21 independent variables plus a value of 1. It is customary to start independent variable lists with an explicit intercept value. So here we're looking at the model table, or the actual model that was created as a result of running the SVM classification function. In order to access the model, we use a SQL select on the model table, just like you would query any other table in a relational database. Since the output can be a little difficult to read in its default format, I also use this /x on option to get the output in a more vertical or readable type format. There is also an unnest option that will render the output in a more readable format. Information about unnest can be found by following the MADlib documentation link specified at the end of this video. So looking at some of the details here, we see that the model table holds the coefficients for each independent variable, along with the number of iterations until convergence, the number of training records processed, in this case nearly 20.5 million records, and the dependent variable labels, either F for false or T for true. The SVM classification function also automatically creates a summary table. The table has a naming convention of the name of the model table with _summary appended, and stores details on the inputs used to build the model. So here we see the name of the source table, the name of the model table, the dependent variable, the independent variable list, edited so that it would fit on this slide, and the fact that we ran a linear SVM. And if you were using or specifying nonlinear SVM, you would see either Gaussian or polynomial here. For more experienced data scientists, the summary table also provides optimization and regularization parameters. And then finally, we see down at the bottom that there was almost 20.5 million training records used to create this model. So with the model built, we're now ready to go on to the next step, which is the prediction step. To make predictions on test or new data, use the SVM_predict function shown here. This function requires the name of the model table created during the training step, the name of the table that holds the test or new data needing predictions, an ID column to uniquely identify each row, and the name of the table to be created to hold the unique IDs and the predictions made. I should note here in the example, I use the same training data for prediction purposes. You would not do this in real life. Since the purpose here is to simply explain syntax, I skipped the customary step of creating a training data set and a test data set. So here we see some of the output from the newly created prediction table. You can join the prediction table back to the test data using the ID column to determine the accuracy of your model. So as a comparison, let's quickly look at the syntax for the training step of a nonlinear SVM. The prediction syntax is identical for both linear and nonlinear SVM, thus you can simply refer to the earlier slide on nonlinear SVM prediction syntax. In this example, the first four arguments, the data table, the model table, the dependent variable, and the independent variable list are the same specifications used for a linear SVM. With nonlinear SVMs, you would additionally specify either Gaussian or polynomial for the kernel trick. Here I chose Gaussian for this example. N components is the desired dimensionality for the transform space. I arbitrarily picked 40 for this example since I wanted something greater than the original 21 variables that I started with. The empty quotes here is a placeholder for a skip parameter. And then we see some optional parameters such as initial step size and max iterations to limit processing in case convergence does not occur within a reasonable number of iterations. For more information about these and other MADlib features and functions, visit the Apache site at madlib.incubator.apache.org. There you'll find the documentation, source code, details on the math behind the MADlib functions, and access to forums and sandboxes. Also, check out Pivotal Academy by going to pivotal.io/academy for access to online and classroom-led training by instructors such as me. I'm Charles Killam, and thank you for watching.